aircraft scatter. Um, this all kicked off as John and Colin will remind me when I said aircraft scatter is not a thing. Um, and where that statement came from was that basically in a former life, in the days of planning communication systems for 99.9999, whatever it turned out to be, percent reliability, the idea of aircraft scatter was basically anathema. It was basically no. Aircraft scatter for me was just something that happened and caused interference. It was not something that one would use as a communications medium. Of course, the minute you go into ham radio, you're looking at all sorts of low probability of time stuff. And that's what aircraft scatter is. That's what meteor scatter is. That's what auroral communications are. They're low percentage of time things, phenomena. And aircraft scatter is basically the same. And of course, I was saying, yeah, it's not a thing. And here we are talking about aircraft scatter. I've renamed it Exploiting Billboards in the Sky. And we'll come to billboards later on, but that's the essence of the whole affair. What are we covering? I'll go straight into a practical example because that then hopefully gives everybody a kind of context of what we're talking about. I'll then have a look at what's involved, what the engineering is, physics of it, a little bit of modeling of aircraft scatter, and then we'll get on to practical tools. How do you actually do it? How do you use it? And then I got a little suggestion later on for the guys down in Sussex. Might apply to the guys up in the borders, that's particularly in the Sussex, because you've got an awful lot of these aeroplanes flying about above you. So that's where we're at, and I'll talk for about 40 minutes, and then hopefully some other people will come in and say, yeah, but my experience is, and yeah, but what about, etc., etc. So open to questions later on. So let's go straight in and let's listen to this. I'll let you listen to it first, then I'll explain a little bit more about what it is, and then we can listen to it again. But just for now, here we go. Okay. That was fun. And I'll let you hear it again. What
Well,
I am
we never
located,
heard it. We never heard anything.
you didn't.
No.
Oh, that's not good. That's not good. Thank you for telling me that.
Well, I heard
I
it
did.
here, so I don't know what's going on.
Well, it's definitely hear it.
We heard.
And in fact, when you put up that the first bit, you know, the screen that you had on earlier, there was nothing on that with the music. There was nothing on that either.
Well, we heard like Morse code.
Yes,
Sounded like Morse code.
that's what you should have done.
Ah.
That's what you
Yeah,
should
we
have
heard
done.
it in Sussex.
Right.
No, didn't hear it in Linfield.
Okay, so
black
I don't
hole.
understand.
Hello.
I don't understand why, because you should be capable of hearing that. I'll run it again and let's just see if we can bottom it out, because it's going out. Sue's hearing it downstairs, and Chris, you're hearing it in the hall. So let's just play it again. Turn your volumes up and make sure that you've not got a local mute applied. I'll give you 2 seconds to just find whatever it is. But just make sure you've not got a local mute where you're muting your own speakers. So let's just do that for two ticks. All right, I'll play it again. Now, what you're going to hear is the Ballycastle beacon. And you can see the Ballycastle beacon over on Northern Ireland. And I am located just somewhere under the C or the K of Hoyk, underneath this EasyJet aircraft. And so you are hearing, what you're hearing is me listening to the Ballycastle beacon on 432 megahertz. So we'll listen again, and quite important, because what I'd like you to hear is something about the amplitude and something about the frequency, the tone, the pitch of the CW. So here we go. Now, did a decent number of people hear that?
Yeah.
Yeah,
Right.
no problem.
So the couple of things that you're hearing there, I'm going to play it once more just to be sure. Look at the S meter on the radio. Look at the S meter on the radio. If you manage to see the elevation on the antennas, you'll be better than I am, because it's that fast. But that's a point that I was trying to make. So let's just play it again. Okay, that'll do for now, and we can come back to that. So we'll look at what we're actually hearing there. But that's me listening to GB3NI, Ballycastle-ish, and we notice there a few things. The signal amplitude, first of all, rises. So it's at a base level for quite a while. And then suddenly up it comes, and then down it goes. So the amplitude rises, and we made on that thing, we made something like about S4, 4S points, something like that. So it came from nothing to 4S points. You can just hear it in the noise, and then suddenly, woof, up we come. We're up to 4S points. If you noticed, I had highlighted EZY EasyJet. There was an EasyJet aircraft above, in front, down the path. My antennas were pointing at 270 degrees towards GB3NI, but for those observant, I was pointing up in the air. I was not pointing at GB3NI. I was pointing in the general direction of, but I was actually pointing up in the air. So the critical thing there is that the amplitude rose, then it fell. The pitch rose, and then it fell. And we'll look at those two phenomena as we go on. So what do we got? What are we actually seeing? Those are my antennas down on the bottom left. And they're not at 60 degrees to the elevation. They're more like 20 degrees just at that point in that photograph. But that's the antennas. GB3NI is on Slievenora, which is a hill over near Ballycastle. And I am obviously just somewhere east of Hoyk. The direct propagation is clearly pointing at the horizon at 270 degrees azimuth. And my antennas are directional. That's the only thing you take from those two things down in the bottom right. Oh, David Smith says, problems with Zoom. Maybe see the next offering. Okay. So all you need to take from the bottom right is that I've got directional antennas, highly directional antennas, and I am pointing up at 60 degrees at the aircraft. And that's the geometry of the whole thing. So we've got propagation by reflection off the airplane, and we've got direct propagation across the path in the troposphere. Now, I'm going to speculate here. S meters are never properly calibrated, but it's something like 6 dB per S point. We've got about four S points. So it's somewhere around 4, 6 is 24, somewhere around 24, 25 dB of enhancement above the normal. The normal is flat. There's nothing there. It's bumping on the noise. And then suddenly, the presence of the aircraft, we're getting those reflections, and we're getting something like 25 dB. That's a lot of gain. That's a lot of enhancement over normal. And this is, in essence, what aircraft scatter is about. You can poke your antennas at another fella, you can try and talk to them, you can try and exchange a data message, but you'll fail. And oh, along comes an airplane and suddenly it succeeds. And if we actually, I could stop at that point because that's the essence of what we're going to talk about here. But remember that there's an enhancement over normal. So we need to talk a little bit about this normal path. In propagation, what is very, 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 very important is you reference everything to something that's normal. For example, if you are propagating via the moon and you are talking to somebody in south of England, if you haven't got 2.5 seconds of delay, in other words, all the way up to the moon, all the way back down again, then you're probably not going via the moon. Your normal path is actually the tropospheric path, and you're managing to communicate over the troposphere, through the troposphere. So very, very important that whenever you're talking about any form of propagation, you reference it to something that we would call the normal path. In this case, it's the tropospheric path. And the tropospheric path is bumping on empty, it's bumping on the noise, and then suddenly we get something up over and above the normal. Here's the path. There's Slieve over in Northern Ireland, and there's Kirkton where I am, somewhere just east of Hawick. There's the path itself. Now, this is us talking about the normal path. We have basically the hills of the borders. We have the hills of Dumfries and Galloway in the way. And then we have the sea over to Slieve has got a wonderful takeoff. But of course, I have a completely rubbish takeoff in that direction. And you can see I have lots of hills in the way. You'll see that the earth bulge is there. It's prominent and it forces the earth up into the terrain, up into the path, up into the direct line of sight. The direct line of sight is the lower green with the kind of lozenge things around it. 225 kilometers-ish, 432 megs, 125 watts out from Slieve ERP. Now, the propagation thing has got the ability for me to say, what chance do you want to communicate? And the answer I put in is 50%. I want to be able to communicate 50% of the time with Slieve or hear it 50% of the time. And the answer is, if that's what you want, then you can achieve that with about a 3 dB fade margin. In other words, a little bit above threshold, above the base. Now, this is the point about the normal path. Hang on. That this path is actually available for 50% of the time. And I remember having a communication with somebody who said, you've got to talk really quickly because they were talking by aircraft. And when I put it in the machine, the path was available. So we have to always reference it back. And the path between Kirkton and Slieve available for 50% of the time. So, however, not at S4. Not at S4. Aha. Replenishing the water. Thank you very much. Oops. Not at S4. At S0. Bumping on empty. The aircraft scatter then enables us, allows us to communicate over a non-line of sight path, over this terribly, terribly obstructed path. The important thing is that we are working here at VHF, UHF, SHF, we're at UHF 432 megs, where the cross-sectional area of an aircraft is very much greater than the wavelength. So the wavelength is 70 centimeters. The cross-sectional area, a radar cross-section, if you're a radar man or woman, the radar cross-section is very much greater than the wavelength. So the size of a 747 is much greater than 70 centimeters. So you imagine a 70 centimeter by 70 centimeter square on the aircraft. The aircraft contains an awful lot of those. Of course, if we're talking about stealth aircraft, then prospectively, the cross-sectional area is very, very low. The radar cross-section is very low. And this is, of course, the great skill in military avoiding being detected, that the effective radar cross-section is very low. But the cross-sectional area, and to throw out a few cross-sectional areas, 747, 40 square meters, A380, 40-ish square meters. Stealth, a stealth jet, 0.001 square meters. The fact that it's huge is neither here nor there. Its cross-sectional area, its effective cross-sectional area is quite low. The important point about this, of course, is when the path and the aircraft track coincide. The aircraft, in this case an EasyJet plane, was above me-ish, above and down the path. And the aircraft and track coincided. I was pointing at the aircraft and I was pointing down towards the beacon. And the important thing, and this will come out again later on, is we have to use a transmission mode which exploits the short window. How long was that window that it came up to S4? 3, 4, 5, 6, what, 8 seconds at the most, maybe? It came up for that. And that's for the duration of time when the path and aircraft track coincided. And if we were going to make use of that communication, that path, then we would have to use a transmission mode that was capable of exploiting an 8-second window. And we'll look at that later on. So, so a little bit there about cross-sectional area and radar cross-section, which we'll come to later on. So what's going on? What's happening? Well, we've looked at the geometry. We know that there's an aircraft up there somewhere above us. I'm trying to communicate, or I'm trying to hear, in this case, the beacon on Slevenora. The result of that, hopefully, is that we can communicate. I'm going to go on now to just look at the electrical science of the whole affair. How does it work? And how do we ultimately exploit it? First thing is that there is no such thing as rays. People love drawing rays from an antenna to an aircraft and back down. I do it. But what's actually happening here is that the energy is diffusing through the atmosphere. It's spreading as it goes, so obviously getting weaker and weaker and weaker. Every time it spreads, it gets weaker. It's the power density is weakened. But the point really is that the energy paints the whole aircraft. So we're not looking at a ray going up and a reflection and a ray going back down. Stop thinking of that. Think of the whole aircraft is painted with energy. The whole aircraft reflects. And that's perhaps the important point. We need to understand a little bit here about what reflection is. Oh dear. What happens when you get reflection is that you send a wave up to the reflecting surface, whatever it is, and the reflecting surface, effectively, to use a wonderful Scottish word, we shuggle up the particles, we shake them up, and those particles re-radiate. So it's nothing else. It's basically we send the energy up, we shake up the particles re-radiates on the same frequency. And therefore, what we have in terms of the path is a free space path loss up and a free space path loss down. And if we only have a small isotropic radiator, a very small reflector, then we will get unity gain. And if we actually do the calculation, we'll do it in a minute, Free space loss plus free space loss down is far too much for us to use. We rely on there being gain. We rely on the fact that that is a big plane compared to the isotropic radiator. And that's the fundamental. So key thing about reflection, we shake up effectively the particles, the molecules of the reflecting surface, and it re-radiates. And we'll look at that again in a bit. Here we are. Here's the geometry of it. The critical thing is, this is why I would dispute why it's called scatter, because there's nothing scattering about it. It does not obey the Rayleigh scattering criteria, therefore it's not scatter per se, but that's perhaps getting a little bit academic about it. Snell's law is just angle of reflection equals angle of incidence equals angle of reflection. And so what we're getting is all parts of the airframe are reflecting. The engines, the fuselage, the wings, and we get a very different reflection pattern if we paint an aircraft that is traveling down the path in the top example, compared to the aircraft traveling across the path. You can imagine that the reflection going down the path is going to be a lot about reflection from the wings, whereas going across the path is going to be a lot about reflection from perhaps the fuselage, and a lot of the wing reflection is actually blocked by that fuselage. So, and we could imagine that we could draw some kind of polar response from the aircraft. People have done it. It's terribly academic. I don't think it's useful for anybody. Basically, we know that the aircraft has multiple reflections. As the saying goes, plurality of reflections, loads of reflections. Every bit of it is reflecting. But if you look at the reflections that are heading off down to the bottom right of the image, you get a lot of reflections in one particular direction. And of course, that's what makes it quite interesting. So we've said that the aircraft is big compared to the wavelength. We've said that it reflects. We've said that each little bit of the, an isotropic radiator, effectively a small part of the airframe, reflects. But the total energy then is the sum of all the re-radiations that are coming off that aircraft, all the reflections. So we're getting quite a lot of reflection, and therefore the plane has gain. And this is the critical point. The plane has gain over the isotropic radiator. That's a bit weird because we normally talk about gain being in an antenna, but the aircraft has gain compared to the isotropic radiator. And we'll come to this and we'll play with it in a few minutes. So getting into the physics then, how does all this play out? All this gain and this reflection. Now, anybody who remembers, I suppose many people will have seen, if you've been around the communications world at all, perhaps 20 years ago, particularly the Americans used to use billboards. Billboards are enormous, flat, sometimes I think bent, metal screens. We might call them hoardings or advertising boards, but they used to put them on top of mountains to reflect the signal. So what you'd do is from the valley floor, you'd poke it up at the reflecting billboard, and then it would spray the energy everywhere. And of course, it would eventually get to the other station. In Europe, we didn't like those because they're terribly spectrally inefficient. But nonetheless, billboards, big things, boards, or an aircraft have gain. And the billboard equation is here, 22.2. Forget that, that's a constant, plus 40 log F. So it depends on the frequency. And at 144 megahertz, it's not so good. 432 megahertz, it's quite good. And at 1296 megahertz, because it's going up, as the mathematicians of you will see, it's going up as f to the power of 4. So at 1296 megs, it's pretty good. So the frequency really for this stuff is 1296 megs. The billboard gain is increasing as log the area squared, 20 log A, and that's in square meters. So we can look at the bigger aeroplanes giving us bigger gain. And then we've got plus 20 log cos alpha. Cos alpha is the included angle. In other words, like that, it's the angle inside my my hands, not the traditional reflection angle, but the included angle. It's half the included angle, and that's quite significant. We'll come to that when we look at how it all works. Anyway, that's all good, but all we need to know is about 42 dB gain for the 747. Hang on to that one. Didn't we say something about 25 dB 4S points above the normal for Mr. EasyJet? Okay, that's starting to give us a flavor from a smaller aircraft to a bigger aircraft. And the total path loss then, 128 dB up. I think that's for something like a 300, 400 kilometer path. 128 up, 128 back. And then we take off the 42 dB gain. And that gets us 212. Why does that matter? Because if we ran with 128 plus 128 and there was no gain, it wouldn't work. And this is absolutely critical. 212, it kind of works. And we'll see the detail in a minute. So let's look now, having got the equations, having said, okay, it seems like it's going to work, let's look now at the path budget and see how well it works for a given aircraft. We use a thing called the path budget. Path budget's like any budget. You spend it the way you like. You spend your power, you spend your antenna gain, etc., and you get a thing like this. Path length, 500 kilometers, frequency 432, free space loss, something, cross-sectional area of the plane, 30 square meters, say, the angle, the billboard gain, a bit more than I said, and we end up down the bottom with a nice green shading, which says, yes, it will work. Yes, we can use, and in this case, I'm using Q65, not FT8, not CW, not speech. I'm using Q65. And Q65 has what is termed coding and bandwidth gain of about 28 dB. That's a lot of enhancement over CW. A very experienced CW operator can manage a little bit below the noise. You can sense the presence of a dot, dash, and just not the presence if you're on the noise or if you're just a little bit below the noise. But you won't get 28 dB. That's 1,000 a factor of almost 1,000 improvement. That won't happen. We're using these machine generated modes, in this case the coding and bandwidth gain of 28 dB. So that's using Q65. Yes, it will work. Now, this is where I should have done something earlier on and didn't. And this is where we have to just hope that I can rescue myself and put up the path budget. This is the one I should have done earlier. 2 ticks. Right, here we go. There we are. Right, now, if all works and I can transfer my screen, I'm going to change it to the path budget screen. And you should be able to see now the path budget screen. Yes, looks similar to the one you saw a few minutes ago.
Yeah, that's the Excel spreadsheet.
Good, good. Right. So we've got a path length of 500 kilometers and we've got a cross-sectional area of 40 square meters. That's the equivalent of a 747. And we've got it green at the bottom. That's all that really matters. If I go to a small aircraft of, let's say, 10 square meters, ooh, nearly falls out. If I go to a Cessna, little Cessna, think it won't work. And if I go to something something like a stealth jet, 0.001, no chance. You can see there the fade margin is negative 70, negative near enough 80. That's absurd. So we need a big plane. We need a big plane, something like a 747 or an A380 or whatever. The angle is quite important because if I were to use straight up and straight down, that is to say 0 degrees, if I actually put in there 0 degrees, oh, it works. Okay, didn't expect it to. It works. If I put in there 85 degrees, which is a glancing transmission, so it's coming up, hitting the aircraft and going down at 85 degrees, then it stops working. And I think the equation actually falls out if you go to 90. Oh, there we are. We've got to 90 degrees where you're glancing. It won't work at all. So we've got this kind of sweet spot probably of equating distance. You want it to glance so that you get greater distance, but you want it to function. So we can go to something like, let's say 70 degrees. And it works. And so we've got the two variables there, the cross-sectional area of the plane and the angle. And the two together give us the billboard gain, and that tells us whether it will or won't work. So in that we need big plane-ish, and we don't want to hit it glancing. We want to hit it kind of a little bit less than glancing, but that shows you the equations that are at work there and the way that they actually work. So let me just go back to sharing and go back to the presentation. Right, and that then summarizes. We're back to where we were. So some of you may also have heard, I should say that I'm using here the billboard equation, and I like the notion of loss up, gain, loss down. You will see people use the bistatic radar equation for all of this. There's nothing wrong with that. It's exactly the same physics. Bistatic radar just says that you've got one transmitter somewhere, you hit the radar, you hit the aircraft, you paint the aircraft, and you receive the energy from that reflection somewhere else, bistatic two static locations. So you will see people use the bistatic radar equation for this as well. So much for the amplitude. That's fine. We're talking about decibels, we're talking about amplitude, we're talking about 4S points of improvement from a small plane, etc. What we now need to look at is what we heard in the example, which was a pitch change. In other words, a frequency change. And we need to think about the Doppler effect. Now, everybody knows the Doppler effect. Police car comes towards you, siren on. As it comes towards you, the pitch rises. As it goes past you, the pitch falls. And that's exactly what you heard in that GP3NI clip at the very, very beginning. So we do need to consider and think about Doppler. Doppler will play havoc with FT8, and FT8 may be pretty useless in the case of this effect. So that's why Q65 is so good, and we'll see that. The Doppler equation up there, the frequency of the Doppler frequency, twice the velocity times the carrier frequency over the speed of sound. Sorry, speed of light, speed of sound. I'm still on police cars. And we're getting about 300 hertz. And we're probably, for a 300 kilometer an hour plane, and we probably heard about 300 hertz on that clip at the very beginning. The pitch change was something like 300 hertz. Looking down the line, TX2RX on the top example, if we are on the aircraft, we will see a Doppler shift because we're traveling away. Therefore, we'll see a reduction in frequency, drop in frequency. But going in from the perspective of the receiver, it's moving, the transmission is moving towards us, so it'll rise. And the net result is we don't get any Doppler effect down the line, or very little, maybe just if we're slightly off the line. But going down the line, in theory, you get a Doppler shift up and a Doppler shift down. The two cancel out. However, for an aircraft that's actually crossing the path, you will see exactly what is displayed in that formula. You will get a Doppler shift, 300 kilometers an hour. You get a 300 hertz change in your signal frequency, and then that can be pretty hectic for decoding. So what about then ultimately the geometry of the whole affair? This is me, and I just put in a friend of mine down in Cambridge, 400 kilometers away. Here's the geometry. We've got exactly the same as we had in the path projection above earlier on. And we can see here that in principle, if it wasn't for the Pennines, I could probably make use of aircraft inside the purple and green zones up at around 15 to 25,000 feet. But you can see there the terrain in front of me in the Pennines is just killing me. It's useless. And therefore, all I can make use of is actually that very small triangle in green. So it is important to know the idea of the path, and we'll come to that when we come to Air Scout, because that's the fundamental of the Air Scout application, to try and predict where aircraft are going to be interesting, useful when we come to aircraft scatter. Let's now look at an example communication. How does it pan out? I've said I used Q65. How does this pan out with a communication using aircraft scatter? And for this, a friend of mine over on the coast, Jim, he and I set up one day and we played around. We dropped the powers and I pointed my antennas up at the sky looking for aircraft, and I'll show you what we got. Here we are. He's over on the coast, GM4 FEM, and there's me. And here's a little aircraft, a little simulation. Here comes a little airplane coming out of Bonchester Bridge. And it's going to come inside the beam width of my antenna in a few moments. And if you count the time that it takes, it literally takes, I think it's 8 seconds to cross. So, 1, 2, 3, 4, 5, 6 seconds-ish. So about 6 seconds. So we've got a 6 seconds window to communicate. I've got a 6-second window to communicate with Jim. And we'll see what happens, because it's quite interesting. Here's what happened. We set up a path which worked with a normal state of affairs at -16, -16 dB below the threshold. And there you are. The timings for those not familiar, this is 14:14 hours, 14:14 and 15 seconds. And this is him receiving me, I think. Yep. And we're registering a signal level of -16. And then 14:45, 15:15, blah, blah, blah. There's the normal path. And then suddenly an aircraft appears. And, well, there we are. Bang, we get 2. So from -15 to 16 to 17, we get +2. So at 14:16 and 45 seconds, we got an aeroplane. And it gave us about 18 dB of uplift. And here we see it in the waterfall display. The normal path is the Q65, for those not familiar. You're getting the sync tones as the bar on the inside the lozenge. You get the bar, vertical bar. These are the synchronization tones. And then the rest of it, the tones are spread across. And you'll see there that you've got 14, 18, 15, 14, 18, 15. we should be negative 14. Then we get to the time 14:16:45, 14:16:45. Woof, we got a huge signal. But we've got Doppler. Look at that Doppler. There are the synchronization tones falling away from left to right over about 100, 150 hertz, something like that. And remember, this is inside 15 seconds of transmission. And there are all the data tones spread out across the to the right. But we're seeing there, the most important thing is we're seeing about an 18 dB uplift. And how do you make this work then as a communications method? So we carried on, and this was this was great fun because we were trying not to communicate. Have you ever tried not to communicate? We're obviously 100 kilometers apart, and that's far too close for 432 megahertz and the sort of thing we're trying to do. So he's got his antennas pointed out into the North Sea. I've got all my amplifiers switched out. He's got all his amplifiers switched out. And we're trying desperately not to communicate unless an aeroplane is coming. And we managed to set it up. And here's the answer. We were overjoyed. Here's what happened. Basically, at 13:46, an aircraft arrived. Remember that we couldn't communicate without the aircraft. We turned everything the wrong way and switched everything off. And we knew that we could not communicate. At 13:46, we got an aircraft which gave us a signal of -7. And this is his receipt of me, he received my CQ. At 13:58, another aircraft came along and gave us -6, and he received my giving him a signal report of -21. And then at 14:12 and 30 seconds, another airplane -2, and we got the RRR, the all received, both. You didn't see the other side of the communication. This is only one side. But he then reports RRR, all received. And we pushed it on to get a 73. We didn't have to, but we got a 73. We needed 4 planes to do the whole affair over 30 minutes to get this. Remember that we've got quite a short window because we're using aircraft that cross the direct path. So we've only got a few seconds to actually get the thing over. And we need 15 seconds to be able to decode. But the important point is that we could do it. We needed 4 planes, and if we'll look in a moment, but basically we needed 4 planes because we only get overhead about 1 plane every 10 minutes. So how did we exploit it? How does one exploit all this? How do you exploit something that occurs like this? Well, what we were doing is sitting underneath Bravo 4. If you look up at the sort of Scottish borders, just on the edge of the London FIR and the Scottish FIR, you've got Bravo 4. That's somewhere, I'm under that somewhere. And these aircraft are going into Edinburgh. They're coming from Gatwick, they're coming from Heathrow, and they're going into Edinburgh. And there's only a plane every 10 minutes or so, 10, 20, even 20 minutes. Sometimes you can be sitting there twiddling your thumbs waiting. Of course, if you're down in the Worthing control area, in the London TMA, then you are going to see an awful lot more aeroplanes. Question as to whether I could exploit it to talk to people in Sussex with data messages. Well, we've already explored that with the prospect of a path profile and said the normal path, the path basically is too obstructed. I've got the Pennines in the way, so that would be giving me a problem. But nonetheless, and I'll come to a presentation in a bit, which does exploit everything. But if you're able to see aircraft, and for example, the aircraft that are leaving Heathrow, and you see the whole lot of them going over the top of Wales, all heading for the States. Hey, if you're on either end of that line, then you've got an aircraft constantly almost, and therefore prospectively, you've got a constant path because you've got always an aircraft above you. Similarly, to some extent, if I didn't have the obstructions up and down the Alpha 1, Alpha 2, etc., straight up the middle of the country, prospectively you could exploit. But you need some tools to do this. Yes, we know there are aircraft up there. Yes, we know that we might like a sked with somebody in Wales or somebody in Frankfurt or whatever. But how do we do all of this? Because it's hardly something that you can actually sit there and call CQ and hope that there's a friendly aeroplane above, just talk to the captain and say, excuse me, can you just do a few circles above where I need you to be? No, we have to have some tools to make this work. So here are those that I would think are useful. The first is the terrain profile, because for me, you have to know something about the normal path, and that's VE2DBE has a site which gives path profiles. So you get a feel for that. You don't have to worry about the maths and putting anything in, just get a feel for the path. Planes, obviously flight radar 24 tells you where the planes are. That's interesting because yeah, you know where the planes are, you know what you might be able to do. The bulletin board run by ON4KST tells you who's on. So if there's somebody saying, hey, I'd really like to have a try at doing some aircraft scatter down into Europe, is anybody up for it? You say that on ON4KST and somebody comes back and says, yeah, I think we can make something work. And so that's useful. The bulletin board is useful. We'll see in a minute Air Scout. You need to know something about which planes are useful. It's all right knowing where the planes are, but you have to know something about which ones are useful. And then I would strongly recommend that if you want to take this any further, that you have a look at John Quarmby, G3XDY's presentation. And if you want to take a quick picture of the screen, if you're interested, that VJ8EX blah, blah, blah is obviously a YouTube. Have a look at what he has to say. He doesn't go into anything that I've gone into here. He takes it on to the next stage and discusses how you might do it with Air Scout. And we'll look at that in 2 ticks. But those are the sorts of tools that you might use. So here's Air Scout, which I mentioned there. Air Scout is computing which planes might give you the reflection. Now, I haven't been able to ascertain this, but it seems to me that Air Scout works on a flat Earth, and that's actually a big error. But Air Scout's the only thing you've got, so you're going to have to get on and use it. The pink aircraft, here's a path between, it's actually between Jim Edgar, GM4FVM, and a station down in near Hereford, G4ASR. And you can see the pink aircraft here. The pink aircraft are the ones inside the pink zone, and they are useful. They might give you the reflections. Now, the good thing is they're mid-path, so they'll give you an awful lot more than 15 seconds because obviously your energy from your antenna spreads. The red aircraft might come good along the way, but we don't know. They might change their track. The grey aircraft are not interesting. They're going elsewhere. And so you can start to see whether aircraft are there between you and the DX station, the station you're going to try and communicate with. So let's try and come to some kind of conclusion. Oh, that's interesting. Okay, let's try and draw some conclusions from this. It's all dependent on geometry. We know there are aircraft up there. We know that if we can predict where the aircraft are, then maybe we can make it work. If the aircraft are of a certain size, preferably larger than a 737 or the like, so the modern day incarnations, then we can make it work. But we have to, of course, have somebody we wish to communicate with. It's not a case of calling, well, it could be a case of calling CQ, but in principle, you would make it work for a net. I then started to think, well, how would you make it work in Sussex? You can see the sort of DX stuff that you might be able to work. And that's fine because John Quarmby described in his presentation how he was communicating down on one of the airways down to Frankfurt. And he's up in somewhere like Norwich, and he's looking down the airway, which is fine. He can then almost call CQ, and he gives an example where he calls CQ in voice, phone, and it works because there are that many aircraft, and an aircraft will sustain him. Remember about going along the path, going down the path. The aircraft sustains the communications for quite a long time. But of course, if you're relying on aircraft going across, that's a different ball game. So how would you make this work in a really simple station? And I just came up with this idea. You guys have got an awful lot of aircraft in the skies. Where would you point your antennas if you were using a Yagi? I haven't a clue. I don't know how you'd make this work. So it occurred to me, and I did a little bit of maths, and it seems to work, is that you've got a lot of aircraft. And so if you were to use that antenna, now that is what they call a paging antenna, upside down paging antenna. Typically, a paging antenna, if you've got a big B&Q warehouse and you wish to use pagers or two-way radios, then you have an antenna which basically fires most of the energy down into the warehouse from the outside. If you look on the outside of the warehouse, you'll see these things, or hotels or whatever it is. Turn it upside down and point most of your energy at the sky. So don't be directional. You've got a lot of airplanes up there that you can paint, and put that with a good view of the sky and use something like Q65. We'd have to use Q65 prospectively. But something like that would be quite fun. And certainly if I was down in Sussex, I'd have a go at that. But I'm up here and we're one plane every 10 minutes. So it's not going to work particularly well, I suspect, in the Scottish borders. But there we are. That's my proposal. That's my tuppence worth to you. Try cross dipoles. You can get them as paging antennas. Strip the front directors off and turn it upside down. Point it at the sky. The only snag is, of course, you have to tell everybody else you're doing that and hope that some other people are there. Conclusions? Right. It's fun. It was really, really quite fun to do it with Jim Edgar. He was a willing participant, and we were turning powers down and trying to make it work, and it was good fun. It's useful for a sked. Somebody at the other end's got to know you want this sked. Calling CQ is perhaps less than useful. Although if you look at the activity contests, I think it's first Tuesday, first Wednesday of every month, you certainly will see the propagation effect in play. And it's most infuriating when I can hear somebody and I go back to them and they're gone. Because, of course, they don't know that I would be there trying to exploit aircraft. As far as they're concerned, they're trying to call CQ to win points. The last thing they're going to bother about is me sitting there saying, hey, we could use 4 aircraft to make this work, etc. Multiple planes are needed, typically, although John Quarmby illustrates that he seems to make use of 1 or 2. And of course, the whole thing is in probability. Is there an aircraft? And have you got somebody at the other end to talk to? So chance rules the whole affair. So there we are. I started with an example, which we heard, the aircraft coming through the path. I listening to GB3NI. I then looked at the geometry of the whole affair, the physics of it, what type of aircraft would and would not give a reflection, an adequate reflection. So big airframe, big jets, good. We then looked at the whole business of how we exploit it and the notion of the sort of pink area up in the sky and the pink aircraft. Yes, we can make those work, etc. And then I ended there just with a sort of little thought of how would you make this work in Sussex? Well, who needs a directional antenna? Just point it up at the sky and paint enough aeroplanes and away you go. So there we are. So that is aircraft scatter. I changed the title here, Hitching a Ride on a Jet Plane. Why not? And at this point, I guess I'll shut up and let anybody else jump in. Over to you, Alan.